Hi, my name's Benjamin Cameron. I'm a lecturer at the University of Southampton in the UK, and today I'll be talking to you about determining plastic material properties from observed heterogeneous strain fields and singularities that arise in the governing equations. So the experimental mechanics community has done an excellent job in the last 30 years developing techniques such as digital image correlation in 2D or digital volume correlation in 3D to get full field kinematic data. The image shows the strain field obtained for a necking 2D tensile specimen. This is true both macroscopically and microscopically, so this shows a strain field of a dual-phase steel. However, in comparison, the information available on the stress is far more limited, and it's typically restricted to cases with homogeneous deformations. This motivates what's called the inverse problem, which is when you know the strain field, but you don't know but the material property is not well characterized, and you don't know the stress field. And the idea is you might be able to solve this by solving the inverse problem. And this is in contrast to the forward problem, which is solved using techniques such as finite element method, etc. You can imagine this would be really useful for high throughput characterization of materials in the case of varying material properties, for high throughput characterization of different stress states, and characterizing the stress in places where it's difficult to measure, such as the middle of a necking tensile specimen. The most common way of solving this is using what's called the finite element model updating, which, as the name suggests, involves running a large number of simulations until the strain field approximately matches what's observed. However, in the case of heterogeneous materials, this frequently becomes computationally infeasible due to the wide range in possibilities. And for more complicated materials, even in the homogeneous case, often the strain field doesn't match within the experimental error, specifically because of the assumptions that are required to go into the constitutive model. So what I'm going to be talking to you about today is a new theoretical view and solution to this problem that's been developed over a few recent papers. And essentially this involves developing a new system of partial differential equations which you can deterministically solve for the stress field. And later on I'll be talking about very recent work on singularities that arise in these governing equations. So to start with, I'll present a simplified form of the theory that's valid in a couple of limiting cases, but then I'll generalize it later. And I should also mention that this theory is currently restricted to isotropic materials, though we hope to extend to anisotropy in the future. So the main assumption is that the principal directions of the stress are aligned with the principal directions of the strain in the case of elastic deformation. If we had plastic deformation with negligible elastic strain, we could also say that the principal directions of the stress are aligned with the strain rate. So just to show what this means, so this is a material element with no strain. We strain it, which we denote by the 2D matrix E, and this has three components, but we can also express this in a slightly different way. We can imagine an angled element, and so there's an associated angle of the strain, which corresponds to the principal direction of the strain, and also two principal strains in the direction of the angle and perpendicular to the angle. And these two ways of expressing it are mathematically equivalent. We can also do exactly the same thing with the stress T. And in the case of elasticity, if the function mapping the elastic strain to stress is isotropic, you can prove that these angles will be the same. Similarly, in the limiting case of plasticity, you can prove that the stress will have the same principal directions as the plastic strain rate. And obviously the strain rate will be equal to the plastic strain rate when there's negligible elastic strain. But let's just take the elastic examples. So we have the angle corresponding to the stress T equals the angle corresponding to the elastic or strain E. So this means that the components of the stress T are related to the components of the strain in this way. But the whole point is we've just done digital image correlation. We know what the components of the strain are. So we can just call this whole right-hand side a variable C that changes with position. We can rearrange this so we have a single equation for the three components of the stress with a known coefficient. But we also know that the stress will satisfy force balance in the x direction and force balance in the y direction. So we have three equations and three unknowns. And we can transform the system using stress area functions into a single equation if we like, though that's not necessary. We can solve this equation directly for the stress, as I'll show. And I just want to comment that we've made very few assumptions. For example, we haven't even mentioned the existence of an elastic modulus or any kind of linearity in the stress-strain relationship. So this is a slightly artificially contrived example where we ran a finite element simulation. And this is a 2D sheet with the blue region, it has this blue stress-strain curve. And in the red region, it has this red stress-strain curve. And in between, it has a in-between stress-strain curve. So we just subject this to tension. And we run the finite element simulation. On the left shows the different stress components, and on the right shows the different strain components. But we pretend we just did an experiment. So we just know the strain. And then we use that and the boundary conditions and solve this equation to get the stress T. And we want to see if it matches the finite element simulation. So the left stress fields show what we calculated by solving the algorithm. And on the right-hand side shows what's output by the finite element solver. And you can see that they're the same. The mean normalized error is on the order of 10 to the minus 4. We can also plot cross-sections of the profiles of the stress. And the gray curve shows the finite element solution, and the dashed curve shows the solution from the algorithm. And we can see that they're essentially an exact match. Because Abacus, or the finite element solver, is solving a nonlinear forward problem, it took a long time, approximately 23 minutes. Whereas this algorithm, because it's linear, took less than a second to solve. So this approach is actually very computationally cheap. And you can imagine if you compare this to running large numbers of finite element simulations, there's orders and orders of magnitude difference. We also made no assumptions about the shape of the stress-strain curve, again, or homogeneity, or anything like that. So I want to get a little bit into the computation, so to give you an intuition for how this works. So the right-hand side shows the body, and at each point we've measured the strain. So we have these boxes which are strained with the principal directions of the strain, and we also have principal directions perpendicular to this. So we can draw lines connecting this, and we have a grid that always intersects at right angles. Now, these lines will be perpendicular to the principal directions of strain, and also aligned with the principal directions of stress. So we can say that no shear stress crosses these boundaries because of those assumptions. So this is very important. Also, we have traction boundary conditions, which is the red curve on the left-hand side. And so the material is getting pulled. For each action, there's an equal and opposite reaction. We can imagine an area of material here, subject to this force. No shear can act across these boundaries. So as the area gets smaller, the stress gets amplified. So you can kind of follow these lines in a directional way and calculate the stress as you go. You can also follow these lines around corners. The equations are just shown here. I don't have time to get into it. And this just shows an example of the characteristic lines for a necking tensile specimen. There are also lines perpendicular to this, which I haven't shown. So we specify the traction on the left-hand side. Then we follow through, calculate the stress on the left of the neck, calculate the stress, follow the lines, calculate the stress in the center of the neck, out on the right-hand side. And you actually calculate the traction on the right-hand side as part of the solution. So you only actually have to specify part of the traction boundary conditions. Sometimes, for some problems, so this is imagine a pipe with a thick-walled cylinder with a pressure inside. You have these characteristic loops going around the circumference. Here, this actually gives rise to non-unique solutions to the equation, so you can't really solve them. And this is because there's nowhere to start the calculation when the characteristic lines forms closed loops. So this is a problem. However, for a large number of cases, this doesn't occur, and the equations are of practical importance. So this is just an experimental example. So we got the strain field at 300 time steps for a necking tensile specimen. This just shows the strain field and the computational mesh. And we solved it using a finite volume method that was developed in a recent paper cited below. And instead of chopping up the domain according to the characteristic lines, this can introduce a little bit of error. We just arbitrarily chop up the domain into finite volumes. In each element, we calculate the principal directions, and we assign a direction of computation. And it's very important to assign the directions of computation consistently. Otherwise, it's really, really easy to get singular matrices, etc., if you don't do everything perfectly. So this code was published as well, so it's freely accessible. And you can use equilibrium between these finite volumes and create a matrix and solve it to solve for the stresses. So these are the different components of the stress that we calculated, and it's a huge amount of data. You can also, so one application of this is you can look at a single material element in the neck, and you know the strain field right through the 300 time steps, the full strain field. You know the stress field right through the 300 time steps. So you can just plot the stress-strain relationship for a material element in the neck. And you can see that you can calculate the material properties up to very large strains, stretches over 100%. You can also do this for elements outside the neck, and you can see that they elastically unload. And this square element just shows the strain at which the deformation was homogeneous, and you can apply classical methods to calculate the stress-strain relationship. But now we can calculate the stress-strain relationship up to this deformation, and these are drawn to scale for an originally square element. This is just highlighting a work by Chang Lu, who's also done a bit of work on this. So the left-hand side shows the angle for an analytical solution of the stress field around a hole. And this shows the characteristic lines that are used for the computation, using a slightly different approach. But essentially he got a perfectly accurate result in the same way. So I've presented the equations for 2D and a couple of limiting cases, but I'd like to show you how this is generalized to a much wider range of problems. So the stress has three principal stresses, sigma, and three principal directions, q. And if we know the principal directions in 3D, using something like digital volume correlation, there are only three remaining unknowns for the stress. And we have three force balance equations, so we can just simply solve these equations, and everything works out in exactly the same way, has exactly the same structure. It's also trivial to add acceleration terms if you know them from measuring the kinematic data, and body force terms. So that's no problem. Also finite deformation, no problem, as long as you solve in the deformed reference frame. And here, in the case of the viscoplastic limit, the stress would be coaxial with the symmetric part of the velocity gradient. And in the elastic case, the left Cauchy deformation tensor. However, one of the most important generalizations that we recently figured out, and this has just been accepted in IJP, is elastoplastic generalization to this problem, because sometimes we don't know which regions are elastic, which regions are plastic, and when we can make these assumptions, especially in a complicated setting with different domains. We know that the stress is coaxial with the elastic strain and the plastic strain rate, but we don't know the elastic strain or plastic strain rate. So this is kind of the problem. And it turns out you can solve this if you assume the elastic modulus, for example, is known. And I'll kind of show you how this works. So imagine, the material's in a state at time t. We have a plastic strain at time t and an elastic strain at time t. So that's just shown on the figure on the right. And we're going to assume we know the stress at time t, but we don't know the stress at time t plus delta t. So we're going to do an incremental calculation. So going back to time t, we also know the elastic strain because we know the elastic modulus. So this elastic strain is actually known. We also have done digital image correlation. So we know the strain rate times delta t, or the step in the strain. So these two things that we know from a triangle. And on the third side of the triangle has two components. It has the plastic strain rate at time t plus delta t, and it has the elastic strain at time t plus delta t. So we know what the sum of these is because we know the other two sides of the triangle, essentially. And we also know that the stress at time t plus delta t is coaxial with both of these variables. So it's coaxial with the elastic strain at time t plus delta t and plastic strain rate. So it will be coaxial with the sum of these two things. So we can get the eigenvectors from the sum of these two things and then just solve for the stress in exactly the same way as we did before. I've kind of explained this in a numerical or finite time step context, but you can take the limit as delta t tends towards 0 and get a system of partial differential equations, which actually end up being nonlinear and time dependent now, unlike the previous setting. So this is an equation for the evolutions of the eigenvectors of the stress. And notice it doesn't depend on the elastic strain or anything. It just depends on the observed total strain rate. And we can combine this with the force balance and other variables to get a complete set of equations. We can do exactly the same thing for the finite deformation case. It just becomes a little bit more mathematically complicated with different reference frames, etc. But that's straightforward. So just to validate this, we ran an elastoplastic simulation. The left-hand side shows the different stress components output by the finite element solver. Right-hand side shows our solution. This is at a relatively early time and at a later time. And they end up being a essentially perfect match again. So these are just cross-sectional profiles of the stress again, just comparing the finite element and our solution. This is earlier time, and this is later time when necking occurs. So those are the generalized form: elastoplastic, finite strain, 3D, etc. But it's still restricted to isotropic, of course. So you may have noticed there was a bit of a hole in everything I've been saying, and that is we've assumed that the stress and, say, for example, the elastic strain have unique eigenvectors. However, when the eigenvalues repeat, they will actually have non-unique eigenvectors, and this manifests as singularities. So, for example, the identity matrix has two eigenvalues of 1, and any vector is an eigenvector. So here we're just going to compare the stress to the elastic strain. We're not going to talk about plasticity for now. So this is shows digital image correlation of a stent subject to different loading by Harshad Paranjabi in 2020. He shared the strain data, and you can look at the difference in the eigenvalues to see where the eigenvalues are essentially the same. So this is just the logarithm. When it's negative, the eigenvalues are essentially going to be the same. So we can zoom in on this region and see that there's a point singularity. And essentially this problem always arises as point singularities in 2D. And it happens in other situations such as bending. This was actually a little bit worrying for me before I did this work, because one might imagine that there's a structure of the characteristic lines around this point. So this black dot shows the point, these black lines show the characteristic lines, and these might form loops. And this is really worrying because if there are loops, it means we can't solve it in the case of these singularities. However, this won't necessarily be the case. There could also be a different structure such as this, or something completely different such as this. So we want to understand this, and what we're going to do is do a Taylor expansion of the stretch tensor around this point, and we're going to look for when these characteristic lines intersect with the singularity, and that's just a way of going through and understanding the structure of the problem. So we're going to use the left Cauchy stretch tensor, and here we're just going to assume the stress is coaxial with this. And the eigenvectors of this tensor will be the characteristic lines at that point, or will be tangential to the characteristic lines at that point. So the stretch tensor has a value b0 at the singularity that's shown in the figure on the right. And if you traverse a distance delta x, we move by delta x dB by dx. And it will have eigenvectors given entirely by dB by dx, because b0 has repeating eigenvalues. So it will have those eigenvectors, and it doesn't matter what delta x is, it could be positive or negative. The orientation of the eigenvectors and characteristic lines will be exactly the same. And exactly the same thing for moving delta y dB by dy. What if we move a general direction? So we move a distance v1 and v2. So this will have eigenvectors determined by the matrix v1 dB by dx1, v2 dB by dx2. And if the characteristic line is, or eigenvectors are pointing exactly towards the singularity, that means they'll intersect with the singularity. So we want to solve for when v is an eigenvector of this matrix. So we have this matrix times v equals lambda v, and for any solutions for that will correspond to lines which intersect with the singularity. And again, it doesn't matter what the magnitude of v is, it could be positive or it could be negative, it will have exactly the same eigenvectors. If we double v, the left-hand side gets 4 times, because you have the v1, v2, but also the vector v. The right-hand side, v doubles, so lambda has to double. So lambda just sets the magnitude of v. So if we want to solve the equations, we can just set lambda equals 1, because we're only interested in the directions. And now we have 2 equations and 2 unknowns. So you see, and it'll be a second order polynomial, because obviously v1 and v2 are multiplying the vector v. And it's going to have coefficients a, b, c, etc. that are given by these dB by dx matrices. So a system of 2 second order polynomial equations. This is relatively reasonably well understood, although there are no nice analytical solutions available. We can apply Bizaut's theorem, which tells us that there are going to be 4 potentially complex solutions. Obviously, we're only interested in real solutions. And we can also note by inspection that 0 will be one of these solutions. So there are actually only potentially 3 solutions that we're interested in. We can use a mathematical technique called resultants to convert this into a cubic equation, a single cubic equation. But I won't go into those details. So if we have this cubic equation where this curve intersects 0 will be one solution. So if this is the cubic, there'll be 3 solutions, or 3 v's as shown, that solve this equation. Each one of these v's, if we traverse a distance out, there will be eigenvectors and characteristic lines given by these crosses. But again, it doesn't matter what the magnitude of v is. So we're going to have all these crosses passing through the singularity like this, and these connect up to form characteristic lines which pass through the singularity. So in the case of 3 solutions, we kind of get this structure of 3 characteristic lines passing through the singularity. There will always be at least one solution, because the cubic has to intersect at one point. So this case is very common, and in very rare cases the cubic might just touch the x-axis and there'll be 2 solutions. So if we go back to our original cases, actually we can see a really positive or hopeful result that this case actually can't occur. So there won't be loops. So this is I think, extremely important result and gives us hope that we can solve this case. This will happen in very rare cases, and this might happen very frequently. So this just shows the structure of the characteristic lines around the singularity in this case, calculated with an ordinary differential equation solver for this example. This shows an example with 3 lines passing through the singularity, and you can see that there's a spider web type structure, and there's for different matrices obviously. And these are just a few randomly generated solutions. So you can see there's quite a variety of structure, though these are reasonably representative. If you zoom out, higher order derivatives of B will become significant, so you'll get a less regular structure. However, when you zoom in, it will always follow this very structured equation. So just a couple of comments on 3D. So we can do exactly the same thing, and it'll just be three equations of second order, which we can solve when all the eigenvalues repeat, and they're going to be 1 to 7 solutions, normally odd numbers of solutions. However, you can imagine that two eigenvalues repeating is much more likely than all three. So this is a very important case also. We can kind of understand how this might work from looking at the 2D case and extending it into the third dimension, imagining a state of plane stress. So these points will actually become lines in 3D. And you can actually show that this will generally be the case for an arbitrary 3D deformation field, though I don't have time to get into it. So can we apply these ideas to actually solve this equation? So one might naively just hope that because of numerical error, the eigenvalues will never exactly be the same, so we might be able to just solve it anyway and hope for the best. But this doesn't work because we have to define the direction of computation consistently. So if for this example we define the direction of computation upward and to the left, we're forced to define it in the same way next door, the same way again as we go around. So we don't have any choices. But when we go the full circle, we run into an inconsistency, which causes unstable matrices, and from a practical perspective, we just can't solve it. Hypothetically, you can imagine if you go right round again, you end up facing the same direction, and we're going to apply this idea later to actually solve this problem. But for any singularity, even if there's very large error, it will have a global effect or a non-local effect on the structure of the equations when you loop round. So you run into this problem. So we developed a solution, and I'm just going to show you with this example of a hyperelastic sheet, which we ran a simulation, got a couple of singularities here. And so you can see that there are these black lines where the eigenvectors are defined inconsistently. So if you go around here, you traverse around the black line, everything's kind of defined consistently. So you can just see that by zooming in. But if you cross the black line, everything rotates 180 degrees. So we're going to use the idea of going around twice and facing in the same direction and introducing another domain here, which you solve the equations in also. So we're going to say that this element is next door neighbors to this element. So it has a bunch of consistently defined next door neighbors. All the elements are happy. Then you traverse around here, everything's smoothly and consistently defined. And then this element will be next door neighbors to this element. So we're kind of solving the equations twice, and they kind of, and every element has consistently defined next door neighbors. And we have developed a computational procedure that will do this automatically for any problem. And we can just apply this with the finite volume method to solve the equations. So on the left shows the stress field calculated with this approach. On the right shows the stress field solved from the finite element computation. You can see that there is reasonable agreement, although there's a bit more error than some of the previous examples I've shown you. And that's because of the high curvature of the characteristic lines. And we're actually in the process of running simulations on finer and finer grids, and we're confident it will converge to essentially the exact solution in the same way. So that's all I have for you today. Thank you for listening, and any questions?